Is my screen visible?
Yes, it's visible. Yes.
Okay. So thank you for inviting me. And today I'll be talking about some natural language interaction with the robot, particularly for task understanding. This image that you show in the backdrop is where you can have natural language interaction with a robot. In this case, this is the Sophia. But this robot particularly doesn't do any task. Uh, it is just for showcase and showing the engineering prowess of uh, mm, uh, muscle movement, facial expression in the robotics field. That was the main purpose. But the interaction capability was just there to show that this is certainly possible and how the facial expressions are curated based on interaction. But in practical setup, we have robots to do certain tasks, and the idea is to you can mm, interact with the robot for task specification, and the robot understands your natural language instruction. More onto that in the later part, but to give you an overview, I'll be talking about some pivotal moment where TCS research has actually started working on robotics as a research area seriously. There are certain historical aspects that probably you'll all be interested, and then I'll briefly touch upon the various robotics research activities that we are doing currently. Mostly the work that we have been doing in last 3-4 years, and we have matured significantly. And then I'll start the actual topic of this talk on interacting with the robot and what we have already developed as a system. And then I'll conclude with the future work. Before jumping into the research part, to give you an highlight about TCS research, we have we have labs in 7 locations within India, namely in Calcutta, Delhi, Mumbai, Pune, Hyderabad, Bangalore, and Chennai. We also have research activities in different research areas. Um, Almost any computing research areas, we have someone working on those areas, and the research activities are grouped into different research areas, and you can see these are the research areas that different people within TCS research work on. I'm part of robotics and autonomous systems group, and the people of this group are spread across these 3 locations: Delhi, Kolkata, and Bangalore. Of course, there are other people in these locations as well, and nowadays most people are working from home, so now you can say people are working all over India. And there is also LinkedIn page and Twitter handle for TCS research. If you look for TCS research in Twitter, you will find our page, and if you search for Tata Consultancy Services research in LinkedIn, you will also find our page. You will get periodic update about different activities. The social media team posts uh, different updates on new paper, or some product development, or some customer interaction, and so on and so forth. Now, I mentioned that there is a pivotal moment in TCS research in terms of robotics. When we started almost 7-8 years ago, I think people have started looking into it even before that. But 7-8 years ago, it was some very focused effort were given to robotics research, and we were looking at some industrial robotics application. And industrial robotics means we probably think of these kind of scenarios. And Amazon, in those days, Amazon used to have these kinds of robots in their warehouse. These are called Kiva robots. So, the warehouses are quite big in size, and they store a large variety of items. So Amazon store these items in racks within their warehouse. These are the racks. And when there is a customer order, the system knows where the object is stored in which rack. And then one robot is assigned to the task of uh, bringing that rack to the packaging location. So the robot moves to that rack location, picks the entire rack, and then brings it to the human worker. And then human worker eventually picks up the object from the rack. If I go forward a bit, yes. So you can see here the human worker picks up the object from the rack, puts the addressing stamp, and then ship it to the customer. And then the robot puts back the rack to its original place. Right. So these were the systems that Amazon have installed some 12 years ago, I think, and now many other e-commerce businesses have also used these kind of robots in their warehouses. Now, there is some problem with these kinds of robots, right? You see that even if only one object is ordered by a customer, the entire rack has to be brought to the packaging location, right? So there is this inefficiency of bringing the entire rack, and then placing it in its original location. This was certainly efficient than completely human-based order picking setup, but still there is a lot of scope for improvement. And that's why Amazon has thrown this challenge called Amazon Pickup Challenge, where the idea is to pick individual objects from the rack. And it is a difficult problem because there are different types of object stored in the racks, and it is very difficult for a particular robotic arm to handle different types of object, right? So there we spotted the opportunity, and we jumped into it, and we participated in the challenge. This is the robot that was developed in our lab. I mean, we bought the hardware, but we wrote the software stack for this picking task. And you see, this is a mock-up of a storage rack where different types of objects are stored, and the arm picks up the object and put it in the basket, right? So we participated in 2016 and 2017. In 2016, if you see the leaderboard after day one, this was a joint team of IIT Kanpur and TCS. We were at the 5th position after day one, but at the end we didn't do that well in that year. In that year, team from TU Delft actually won the competition. I graduated from TU Delft, so something to be proud. In 2017, though, we did quite well. At the end, we did podium finish. In one challenge, we secured the 3rd position, that is the pick task, and overall we secured 5th position. If you look at the point, our final score was 170, and we did better than the team of MIT and Princeton, and something to be really proud of, right? So now imagine this kind of technology becomes mature, which is now actually, So the robot can pick individual objects from the storage racks. So what can now be done? The robot need not bring the entire rack from the storage location, but it can pick individual object. So in terms of task completion or task allocation, what used to happen earlier was, if you look at this left hand side, the robot starting from the origin go to the task one location or the storage rack location, brings bring the entire rack to the packaging dock, and then it can go for next task, right? Now what can happen, the robot can go to the task one location, pick the individual object, then directly go to the task two location, pick the second object, and then go back to the packaging location. Or it can go and pick a few more objects considering its capacity and the demand of these objects. So for example, the robot can carry 20 kilogram at max. So all the objects it is picking in one round should not cross 20 kilogram, right? So this is this leads to a new kind of task allocation scenario, and this has to be dealt efficiently, because we are talking about hundreds of robots and thousands of tasks, and any inefficiency to this task allocation mechanism can have severe impact to the overall operational cost of the warehouse. So this problem, this task allocation problem can be mapped to a classical computer science problem called CVRP, or capacity constrained vehicle routing problem, which is known to be an NP-hard problem. And no exact algorithm or optimal algorithm exists that can solve the problem optimally when there is more than 100 nodes or 100 tasks, right? And there are heuristics algorithms, of course, but again, the efficiency of the heuristic algorithms decreases when there is more number of tasks and more number of agents. And so far, the problem instances, the practical problem instances that people have dealt, there are few hundreds of tasks. But now we have a problem where we have thousands of tasks. So we need to have a, even if it is a heuristic algorithm, it needs to be much more scalable, so that hundreds of robots and thousands of tasks can be handled. So we worked on it, and we developed an algorithm called NCAR. And if you look at the performance comparison, there is a Google OR toolbox, optimization toolbox, that you can use for solving this kind of problem, particularly CVRP. The y-axis shows the cost of the solution in terms of total distance traveled by all the robots to complete all the tasks, right? And the x-axis showing number of tasks. N is the number of tasks, K is number of agents. When there is relatively less number of agents and less number of tasks, you see our algorithm is almost comparable with OR tools solution. But as the number of agents and number of tasks increases, our solution is better. The lower the cost, the better the solution. Okay. Now, let me show you a demo how this system works. Let's assume this is a warehouse scenario where these rectangles are the storage locations, and these gray circles are the task locations, and there are a number of robots currently locating at the packaging area or packaging dock, and each round a robot is assigned a certain number of tasks, and so you see the green robot, if this green one is a robot, and these three green dots are the tasks assigned to it. So the robot goes and picks up the tasks assigned to it in this round and comes back to the packaging dock, then goes for the next round, and these things continues over time, right, until all the tasks are completed. So this is a wave of tasks, that is the tasks that are accumulated over a period. Once this wave is completed, the next wave of tasks are imported to the system, and then they are scheduled, right? So you see that our solution finishes all the tasks much faster with less distance, and state of the art takes a bit more longer. So that is the as I mentioned, this Amazon Pickup Challenge actually actually a pivotal point in robotic research within TCS, and it showed that we have the capability to build a state-of-the-art solution, and we can compete with the players in the market. And over time, the research activities has progressed in other or branched out in other directions as well. So if I have to now list down the kind of research activities, these are the some activities that we are doing for over last couple of years and has become a lot more mature. In the multi-robot system domain, we do multi-robot task allocation, multi-robot coordination. We participated in Embodied IHFC challenge, Embodied IHFC 2020, and we finished in the top 10 teams. And then we do simultaneous localization and mapping, drone navigation. There is cloud robotics, that is it is a framework for multi-robot task allocation, coordination, and all that. Then we also have developed a robot hardware called pal picker, basically a picker much similar to the Kiva robots that you see in Amazon warehouse, but it has a extended set of features and a lot more functionalities for smart warehouse. Then we have some exciting work on remote assistant space, where we are working on telepresence systems as well as teleoperation. In terms of teleoperation, we have participated in NX Prize 2021. We cleared the semi-final round, but we could not qualify for the final, where only 4 teams were qualified. But overall, we did quite well in this competition as well. So let me show you this video where you will see some of these in action. So this is the telepresence robot that we have. Obviously, we didn't build the hardware. We bought the hardware, but we wrote the stack. This robot you can use for remotely attending a place. It can be a conference. It can be a customer visit to our lab, or a customer visit to a site, or an expert visiting a remote site. The telepresence robot has certain features of map-based navigation, manual navigation. So here is one example where you see that the person is showing something to the robot, or basically pointing go that direction, and the robot is actually following that. A similar view you can see here, where just pausing here. Here the robot is being used by a remote participant to interact with a group of people, and based on the speaker based on the sound source, the robot turns towards the speaker so that the remote viewer can actually see who is actually talking. Yeah, sorry. Yeah, and here is the pal picker that I talked about. This is this is an in-house robot picker that we have developed, and this can be used in various warehouse setup. Now I have mentioned various lot of things. My work is mostly focused on multi-robot task allocation and human-robot interaction. Some of my work on multi-robot task allocation I have shown, but now I'll be moving towards this human-robot interaction part. Before I move into this part, is there any question? You can ask, otherwise I'll continue and you can maybe ask later at the end. No? Okay. Let me continue then. So in this multi-robot setup, what we have seen is the robots are working mostly autonomously. Robots are used in industry for let's say 50 years now. Particularly in manufacturing setup, the robots are used, but they were mostly in the caged setup. On the left hand side, you see a picture from Tesla factory where the robots are used in car manufacturing, right? But you see there are these caged, these safety fences were installed so that there is no accidental harm with the caused by this robot to other human beings. So these robots will stay, and we require these robots. But nowadays we have other kinds of robots where robots are much more like a cohabitant, right? So the robots can be in our home or even in shop floor, factory floor, right? And when we have a cohabitant robot, there is a scope for interaction with the robot, right? So probably we have seen where robots are used in restaurant, robots are used in airport. Nowadays, particularly during pandemic, robots can be used in hospital as well, right? So you have seen this telepresence robot, and these robot can also be used for either for elder care. A doctor remotely attends a group of patients, so the robot need not visit the hospital facility. It might be in a remote area, but the through the robot the doctor can attend all the patients, right? So in all this setup, there is a scope for interaction with the robot. For example, let me give you this setup where you say can you go near the vending machine. The human being say, can you go near the vending machine in the hall, right? So the robot then has to move to the vending machine in the hall. We as a human being understand what to do, right? But for a robot or a computing system to understand and perform this task, it has to understand what is the intention behind this utterance, right? So the robot has to understand that this is a moving kind of task, and this word go actually signifies this is a moving kind of task, and the movement should be in an area where the vending machine is residing in, right? So the robot can move to this area, and then while getting closer to the area, it identifies there are two vending machines. One is blue, one is red. The human being said go near the vending machine, but it didn't specify which vending machine. Maybe the human being was not aware there are two vending machines, or he or she forgets there are two vending machines. So the robot asks, I see a blue and red vending machine, which one you are referring to? And then the human being responds and the robot can act accordingly, right? using this can be a in place robot. That means the human and the robot in the same place, and the robot moves to another room or another area. Or this can be a remote setup as well. For example, this can be a telepresence setup. The human being is remotely connected with the robot, and the human being wants the robot to move to some location. Instead of driving the robot manually, because that is cumbersome, the human being has to be aware, or has to be familiar about the environment. So it is better if the human being can instruct the robot in high level goal, and the robot can perform it. So in all this setup, this interaction comes handy, right? But the question is, how can the robot deduct a natural language instruction and execute the task? So this same instruction can be given in various ways. Can you go near the vending machine in the hall? You can say, go near the vending machine in the hall. Go near the please go near the vending machine in the hall. Or you can just say, go near the vending machine, go to the hall. All these are similar kind of task, but has slightly different utterance, as well as the activity can be slightly different. So all this has all this leads to this problem of task understanding or natural language task understanding. So if you look at the research challenge in it, I already mentioned that there is a large variety possible for the same intended task, and the same task can be coupled with a number of parameters. For example, if it is a moving kind of task, the movement can be to a different location. So the robot has to ground that in its environment. So I say, go to the hall, the robot should understand that this is a moving task and it should move to the hall. Robot should understand what is a hall. If I say, go near the bed 21, so the robot should have, or should have should have the understanding that which one is bed 21, right? So that has to be figured out before the robot can execute the task. And if it cannot figure that out, then it cannot execute. So what can be done in that scenario, right? So there is a gap of understanding, processing the natural language and instruction, and then actually generating a executable plan that the robot can perform. I mentioned natural language is ambiguous, so ambiguity has to be dealt. Um, what what happens if the robot fails to understand? So if I say something that the robot cannot understand, then robot cannot execute. So robot will just sit there, or say, sorry, I cannot do it. Is it a desirable thing? A more desirable thing would be the robot can try to clarify it, right? So the robot asks a suitable question depending on the scenario, and then the human being answers, and that should probably help the robot to understand it, right? So a bidirectional conversation is necessary. Mm, On that aspect, we have developed this task conversational agent for robot, or TICA. This is a task understanding and plan generation system, and it is coupled with a dialogue engine. If the task is understood and a plan can be generated, the robot executes it. If it faces any problem, it asks a suitable question, right? So the goal of Tinker is to map the skill of the map the ambiguous and unseen vocabulary present in the sentence to the skill set of the robot, and whenever required, it should ask the question. There are a couple of publications associated with this task. If you are interested, you can have a look at them. So what we do is basically we have a tagging model. So the words are tagged as a predefined task type. So we created a conditional random field based, conditional random forest based classifier for task prediction. So in this case, the bring me the pen from the table, all these words are tokenized, and then the word bring is classified as a bringing kind of task, and rest of the words are ignored for this task classification problem, right? Once we identify the task type, we know that we have a slot filling mechanism. So for each task type, there are certain mandatory and certain optional parameters. So for a bringing kind of task, you have a source location, you have an object, you have a source location, and these informations has to be identified from the instruction, right? So then another CRF is trained for this task parameter prediction. In this case, the pen is the object, and from the table is the source location, and to the speaker is the goal location, right? So we create a predicate out of this sentence, and then we ultimately we generate a plan, right? In this case, all the informations are available, so the system generates the plan, and the robot can readily execute the task. Now take this scenario where conversation is required. You say, take the book and bring it to the desk, right? So if you parse the sentence, you see there are two tasks here. One is taking and one is bringing. So for the taking task, you have the object, but the source location is not there, right? For the bringing task, however, you have the object and the goal location and the source location all clear, because the source is the book location that you get from the taking task, right? But the source location for the taking task is not clear. So you ask a question accordingly, from where should I take it? And the answer is take it from the table or any other variation of it. So you get the required information. Now you can generate a plan, and then the robot can execute it. Obviously, the question asking of question depends on the context, and so it is not a fixed kind of question asking all the time. Let's take this example. You say, bring me the pen, and this is a bringing task. You know the object is pen, but from where should the robot bring the pen is not clear. In that case, the robot should ask, where can I find it, or from where I can bring it, right? But if you have a slightly different scenario where you first say, pick up the pen from the table. So this is a picking task. The object is pen, and it should be picked from the table. And now the robot already have the pen, right? Next, if you say, bring me the pen, so the robot already has the pen, so it need not ask, where is the pen, right? So in that case, it need not ask any question at all, and it can execute it. So the question formulation or question generation depends on the context. Similarly, for different types of task type, so a same word, it's certainly not a word or string matching kind of mechanism. The same word or same verb can be used for to specify different kinds of tasks. For example, you can say turn on the TV, and that means you have to do the state change of the TV. Or you can say turn left, so in that case it is a actually turning, the rotate should turn towards the left, right? So how can we deal with those scenarios? Obviously this is a learning based mechanism, so if our model are trained with certain variations of the data, then the model can predict it accurately. So now the question is, if the robot asks question, what strategy should it follow to ask question? In other words, how should the question framing be done so that the human user actually understands and can answer, so that the robot can also resolve the issue, right? So there are certain ways you can ask question. One is rephrasing, one is clarification, and clarification can be explicit or implicit, right? So and we figured out that implicit clarification actually helps, and that's how we also developed our dialogue mechanism. So what is our dialogue policy, right? Or in other words, when we are actually going to ask the question, remember we have developed a classifier for task prediction, right? So what happens is the classifier actually assigns a score to the predicted task type, right? So when you say something, the classifier predicts what could be the possible task type and also assigns a score. If the score is below certain threshold, you ask a question, or sometimes it is suggestive question. You ask a question regarding the top score task, that do you mean this task? If the answer is negative, then you ask for the next best, right? And you keep on doing this. Obviously you cannot keep doing this for infinite number of times. That will actually impact the user experience. So there is a cap that after 4 times you say, okay, I cannot understand this task, sorry, right? So that is the dialogue policy. And a similar policy can be adopted by seeing the, sorry, okay, a similar policy can be adopted, but instead of classifier score, you can use a different mechanism of let's say synonym based. WordNet is one such resource where you can look for similar kind of word, and then from there you pick the best matching task type, right? And then you can ask accordingly. But as we have seen that that is not the best strategy, and our strategy works better in most of the cases. If you look at this comparison table, the number of questions, the x-axis is showing a different verbs. Here the verbs are actually signifying different task types, and we have two different types. One is novel verbs, that is the unknown verbs. These verbs are not seen during training, and ambiguous verb, that is the meaning is not obvious or meaning is not clear. And the y-axis is showing how many questions are asked to actually resolve the scenario. And you see that our setup, our system is resolving the scenario by asking minimal number of questions, whereas WordNet asks more questions to resolve the setup. So this is the example scenario, an example demo. This is a on the left hand side. Let me just pause it. Sorry, where is the pause? So the right hand side is showing a meeting room setup where there is a corridor and a meeting room with a table, a couple of chairs, and this red dot is the robot. And there are doors. One is front door, one is meeting room door. Initially, the robot was in the charging dock, and you can instruct the robot to do different kinds of tasks, move to a location, change display, turn on, turn off, go near the chair. And if the robot understands the task, it performs. It cannot understand, it asks a suitable question to resolve the thing. And this is the setup we use to demonstrate the efficacy of our system. Now, to a more practical setup, where we have this installed in the robot, in our telepresence robot. This is the telepresence robot in one of our colleagues' home. So we instruct the robot, can you bring the bottle from the dining table? So the robot understands that this is the task type, and this is a bringing kind of task, and it should bring a water bottle from the dining table, right? Red water bottle in particular. So it moves to the dining table location, assuming the robot already knows the location of the dining table. And then after reaching there, so at the initial phase, the robot didn't face any issue understanding the human intention. So it starts executing. But while doing the task, it reaches the location and it sees these objects in the at the location. So the initial instruction was the red water bottle, but there is no red water bottle, right? So it asks a suitable question to resolve this scenario. And in this case, it says, I see a yellow water bottle. Should I bring it? Right? If the user says okay, then the robot performs that. In this case, the robot actually don't do this because it doesn't have any arm, but just to show the proof of concept, this is how the system works. As I mentioned, user experience matters in this kind of setup. So the question asked by the user, whether the robot could understand it, or the question asked by the robot, whether the user understands it, all these are a factor in terms of user experience. So we did this study, and we asked questions. We did this survey. So when the scenario was what the robot says, in those scenarios, human being understood what the robot says. But when the human being says something, it is perceived that the robot could not understood what the human being says. So there is still a scope for improvement. So if you look at this part, that robot understand most of the answers I gave. So a large percentage of person disagrees that robot could actually understood what the human being says. So there is certainly scope for improvement. So as a future work, what we can do is certainly we can think about much more complex instruction, and how can we generate plan for those complex instruction. The use case scenarios that we have taken so far, where human and robot are not co-working together. So in the cobot scenario, the interaction it can add a additional dimension, that is the real timeness. So that can be another area of future work. For interaction, we didn't follow much of the social norm. That means how the question is being formed, whether it is socially acceptable or not, and that actually impacts the user experience. So those things can be looked into thoroughly. Similarly, after understanding whether the execution is actually as per user intention or not, that is also a thing that we should look into in future. That's all I have to say for today. I should certainly thank my colleagues. There are some more people with whom I have worked, but these are the people I should certainly thank for all this work that I briefly presented today. Thank you very much. And yeah, time for questions.
Thank you, Dr. Chan. So we are open for questions now, and we have our first question. S. Right? I don't know the name. You can go ahead.
Krishna. Okay. Hello. My name is Sri Krishna. I
Okay.
like to ask question. You had
Thank you.
a telepresence robot, right? Can you tell me? You said you had bought that robot. Can you tell me what robot that is? Like, is it commercially available?
Yeah, it is commercially available. It is called Double. This is Double 2 version 2. They have Double 3 as well. We have Double 3 as well. So if you look for Double, DOUBLE, Double Robotics, that is the platform we are using.
Okay. Thank you. Thank you.
Yeah.
Thanks.
Yes, Shraddha ma'am, please go ahead.
Hi. So my question is regarding the interaction with the robot. So
Hmm.
you just gave an example. Suppose we ask our robot to pick up a red bottle from the table. So can if such a scenario happens, suppose two persons speak at the same time. If suppose
Hmm.
two persons are in the room and they give you, one gives you red bottle and another one gives you could some another command. So will it cause confusion to robot, or how will it give precedence to their commands?
Yeah, so that is certainly a factor. We haven't dealt that explicitly. What we have is at this point explicit right over the robot. We have that system in the telepresence where multiple person can log into the robot, but at one point only one person can control the robot. So control means only that person can issue a command. But if it is a co-located setup that all the two person and the robot is at the same place and both the persons issues command, then whom should the preference should be given? That is a sort of social aspect that the robot should learn. But yeah, so far we haven't dealt that. But yes, that is certainly a valid point.
Uh, Okay, thank you, Chayan. One more thing I would like to ask. If the command is given to pick up the bottle, so will it be picking up also? Or it's just interactive and it will go and stand there, because I couldn't see the manipulator arm in front of that telepresence robot that was in your colleague's house.
Right. No, in this case, it is not going to do because this is a telepresence. We have teleoperation as well, where the robot is with the arm. But for telepresence, it is just the remote presence, and in terms of activity, robot goes from one location to another location. So if the robot has arm, then it can pick. In this case, the idea is to prove whether the instruction is understood, whether the situation can be analyzed and the questions can be asked properly. The robot can raise a proper question or not, just to prove that concept. But yes, this robot will not do, but we have a telepresence robot where it is with the arm, and there it can pick.
Okay, thank you, Chayan. Thank you.
Yeah. So just to add a point there, just a minute, let me find this. Yes. So here I mentioned this telepresence and teleoperation. So in this teleoperation, we have used this Sophia robot. Again, Sophia doesn't have arm. But we installed a manipulator, and also Sophia is static. So we have developed a mobile base and an arm, so that it becomes a teleoperation platform. That's what we have built, and that
I would
was
like to
used
ask
in this.
one thing more, Chayan. You just told that you have developed a mobile base. So is it
Right.
available in the market, or it's like just for the research purpose? It is with TCS only right now.
Yeah, it is with the TCS, and it can be. I don't think it can be. It is sold in that sense, but we are selling it to customers, not as a single unit, but multiple units can be sold. That's how it is at this point. But if you are interested and if you are looking for something like that, something can be. We can see whether that is possible or not.
Okay, okay. Thank you so much. Thank you.
Yes.
Well, I have a question. Oh,
Yes.
am I audible?
Yes. Yes.
Okay. Thank you, Dr. Sarkar, for your nice talk. This is Professor GC Nandi. I'm from Center of Intelligent Robotics, IIIT Allahabad. I have a couple of questions because we are dealing a lot of synergies are there. What you talked and what we are doing actually in our center.
Right.
We are doing experiment in grasping and warehouse robot. In fact, we have a project under IHFC. Recently we got. So we are experimenting with Bextra type of collaborative robot. My first question was actually the robot picking was on grasping was tabletop, or it is 6D based on 6D pose. Means when you instruct robot to grasp yellow bottle or something like that, you are solving tabletop grasping problem, or is it a 6D pose based problem? Number one question. Second, these technologies which you have discussed, are they in the laboratory, or they are also you have implemented in some actual warehouse? And yeah, please.
Yeah. To answer your first question, I personally don't work on the manipulation part. I work on the interaction part only. I know people are working on both the setup, tabletop, as well as on a mobile base or 6D. I think that what you mentioned. I'm not the best person to answer this. If you need further information on that, I can certainly connect with you. But yes, we have people working on that. On the second aspect, we have proof of concepts, as well as we have some demonstrators that are used in practical setup. We don't have anything yet in terms of manipulation that is operational in warehouse, but we have this picker that is operational in warehouse, not the manipulators. But we have demonstrated that in practical setup, but so far we don't have any customer on that aspect.
Okay. Got you. Thank you.
Yes. Thank you, Dr. Sarkar, and for the questions also from the audience. So now we'll move to our felicitations part. So I would like to call upon Professor Saha, if he's there.
Yeah.
Yes. And to felicitate our guest speaker with a 150 euros Springer reward voucher. So, and Professor Saha, if you can just share some
Yeah.
words.
Just before that, so thanks, Chayan, and sorry, I was not able. We had a new director today, and he was talking to the faculty. So I was listening to him. So and TCS anyway is our good friend, and as I saw the last 5-10 minutes, no, the lot of synergy can be done, and Rajesh's group is anyway working on the healthcare robotics with us. So we'll find
Right.
offline many more synergies so we can bring it out. So
Sure.
it is a token of appreciation from our side. 150 euro. It's sponsored by Springer. So please accept it. I didn't have that animation here, so please accept it. And Udayan will share how to get this voucher encased or get the book or whatever it is. So thank you for coming and sharing very beautiful work. The last part I saw at home, the robot was moving around. So that's quite impressive. So
Yeah.
thank you and all the best. Yeah.
Yeah, and Professor Saha, one thing I would just like to mention, what
Yes.
Dr. Sarkar presented today,
Mm.
we have lots of synergy. So can we talk
Please.
in future?
Yes.
Means for our, as you know, we are our project is also in that.
Get him in your grand projects in that case, no?
Yeah, yeah, yeah.
So,
That will be very nice.
so
So
in
who will
other
be the person with whom we can actually
yes,
talk? That
in
will be very.
healthcare already 30 lakhs they would be investing from their side. So maybe you can rope in Chayan and his group, no? So in your project, so I think it will be good synergy. Yes, sure. Thank
Okay,
you.
very good. So, Chan, you have an email address or something? You can.
Yes, yes. So I'll just type it here. You can reach me anytime.
So
Sure.
you are from what? Kolkata or Bangalore? Which one?
No, right, I'm in Delhi.
You are in Delhi, Acha. I
Oh.
was so last time I visited, probably we didn't meet. No. So when did you
I
start
used to
working?
be in Calcutta lab, but last year I moved to Delhi.
Okay, so please come down to Delhi, our campus once. No.
Sure, sure. No, I have visited campus. I have started working with Rohan Paul, Dr. Rohan Paul from
Yes,
CSE.
yes,
Yeah.
yes.
So
Okay.
yeah.
Thank you. So Udan.
Yeah, thank you everyone, and thank you, Dr. Sarkar, for such a wonderful talk.
Thank
And
you.
so he has already shared his email, and if any of our audience members is having further questions, they can maybe reach him through that. Will it be fine?
Yes, yes.
Okay, thank you. So with
Okay.
this, we'll wrap up today's session, and we'll meet you again in the next month. Thank you all for joining in.
Great.
Thank
Thank
you.
you. Thank you.
Bye bye.
Bye bye.